I mentioned that we have three parts to running any machine learning algorithm. First, we had to prepare the data, and we're going to see lots of other examples in the next case studies of doing that. Second, we have to train our model. We went into a lot of detail on that. So by now you should have a pretty good intuitive understanding of what deep learning is actually doing under the hood. If you don't understand all the math, it's okay. You'll still be able to grasp what's happening. We can get much more detailed here, but the amount of math we did go through will give you a good foundation to develop that intuitive understanding in more complicated examples. When we compiled our model, we asked it to keep track of an accuracy metric. This is basically a measure of how many classifications we got correct. A correct classification is a yes or a no question. Either we got it right or we didn't. We also saw that the accuracy increased with every epoch, and if you kept track, with every mini batch, as we can see as this model is being trained. And the third part is evaluating our model. We used two functions to assess this. The first just asked for the metrics, so we had access to the loss and accuracy, and the second was the predict function that allowed us to match the predicted values to our actual values. This is a pretty basic data set, so what do you think would cause our model to incorrectly identify the digits? Let's take a look at some particularly tricky images and their misclassifications. There are two reasons why these images are incorrectly classified. First, there are always going to be some inherent ambiguities. There are some digits which just look similar. For example, 4 and 9 look very similar when written. So it's not surprising that they're often misclassified. We kind of think of this as a kind of systematic error. No matter how large our data set is, we'll still have a hard time dealing with this, but there is a solution. We can improve our performance by building a better network. Remember that we're just dealing with the end phase of a much more involved convolutional network. We'll address this in the second part of the video series. The second problem is that there are always going to be some rare cases that we just didn't see in the training set and so couldn't properly prepare for. We can think of this as a type of random error, since if we had a really large data set, we'd eventually see them. But even with 60,000 values, we still didn't get every rare occurrence. We can expect that there are always going to be some rare occurrences that our model has never seen. A useful way to view your results is to create a confusion matrix. This is just a plot where we list all of our actual values on the x-axis and all the predicted values on the y-axis. I've left out all the correct matches, which would appear on the diagonal line. Instead, we're interested in the upper and lower triangles. That's where our actual and predicted values don't match. Instead of drawing a dot for each value, I've just drawn a square proportional to the number of cases. As you can see, 4 and 9 are easily confused, as we would probably guess, but there are lots of other misclassifications which tell us that our model isn't as good as we thought. But we already knew that. Remember, this is actually a computer vision problem, and our network is pretty simple. We're just using it for teaching purposes here. Let's take a look at a published confusion matrix, which use capital and lowercase letters of the alphabet. I really like this example because we can see clear patterns. There are two diagonal streaks where we find easily confused upper and lowercase letters. So at least here we can understand why this model missed those matches. The items outside these two diagonal lines are other commonly confused characters, like lowercase l, which is predicted as uppercase I. That confusion alone accounts for 9.5% of the error. I'm going to wrap up the MNIST example here. You'll find the code to create a confusion matrix of your MNIST run through in the markdown file. For now, I'm going to wrap up with this example. We covered a lot of material in this unit, so before I move on, let's briefly review what we've covered in our deep learning landscape in the next module.